and it is favored by proliferant states. And I think the simple idea of it, it's like a spinning top, but it's spinning at least 300 meters per second, and it can spin up to 1,000 meters per second if it's an extremely advanced one. And so it's very difficult to make, but it was the secret of it. And you can see in this picture the little pin at the bottom. The secret of it is that it's self-stabilizing, that it doesn't tip over when it's spinning. If it moves off center a little bit, it tends to return to the center, and it's helped in that by some magnets that are at the top, which I'll show more detail a little later. So it was quite an ingenious invention, and it was designed to not require much energy to enrich. The vacuum, you want to have a vacuum along the side, because if it's spinning that fast, air friction can be tremendous. If there wasn't a vacuum, it would just heat up and I guess disintegrate. And so you have to create a vacuum. But the idea and it was developed in Russia, the idea of the Russians, along with their German compatriots, captured German and Austrian scientists, was to make it basically they call it a molecular pump, and it's a stationary object. And so the spinning is done by the rotor, and that actually generates the vacuum, a higher level vacuum along the rotor, sides of the rotors. The whole system is under vacuum, but there's extra vacuum created by this molecular pump. And also, there's one design weakness in the centrifuge, where you have to have a hole in the top to get the enriched uranium out, to get the feed material in and get the waste out. And the enriched uranium or the natural uranium can leak out the top. And so the molecular pump also keeps that material from going down the sides, keeps it up at the top, and therefore keeps the vacuum intact. There's a concept that I'm not going to cover called countercurrent flow, which if you look at centrifuges is important. The spinning by itself isn't enough to get much of a separation. Like the atoms or the mass, uranium-235 versus 238 is going to separate based on its mass when it's spinning, but that's actually not enough. And you actually have to get the gas flowing up and down. And in doing that, some mechanisms come into play that actually create most of the separation of the isotopes. And you get a separation where one end is concentrated in U-235, the other end is depleted in U-235. And so from an engineering standpoint, that's great, because then you can stick in a little device. It's called a scoop. It's just a tube that impinges on the gas, and the gas goes into it. And so if you have the enriched at one end, the depleted at the other, this thing with the idea of a scoop can work quite well to pull out the gas and the waste, or the enriched material and the waste material. Now the separative output, remember the separative work units, the SWU, there are two variables that decide fundamentally the power, it's called the separative power of a centrifuge. The first is the velocity, and the separative power is proportional to the velocity squared. And the other parameter is length. So the idea is spins faster, higher separative output or power. If it's longer, same thing. And so the whole development of centrifuges is to get these things to spin faster and to make them longer. They're not, and the separative output isn't directly dependent on the rotor's diameter, but there is some indirect dependence if you're actually building centrifuges and you want to get the separative length up, the separative power up. Centrifuges operate at moderate temperatures. Essentially, let's say 300 degrees Kelvin. And there's a simple formula to give you, we call it in ICE a maximum separative output. One of our consultants at UVA derived it. So it's a simplification, and some of the formulas to derive separative work of a centrifuge are very complicated and require inside knowledge of the centrifuge, which is often either classified or proprietary. And so this formula is an open source formula that's independent of these particular data that's secret. But what you end up with is it's a maximum estimate. It's not the actual separative power is going to be less in an actual situation. But if you want to scale between types, this is a very effective formula. And if you want to just compare different speeds and lengths, it works quite easily. Now I mentioned you want to get the speed up. Well, that really depends on the material. Some materials can withstand higher speeds, others can't. And at some speed, all these materials are just going to fly apart. The first material developed for centrifuges was an aluminum alloy, and it could have a speed up to 445 meters per second, but aluminum has an undesirable property that when it's spinning, it tends to creep and move. And what that meant, if you're up at the higher speeds, the centrifuge will break within a year. And so the operational speeds of these aluminum rotors are down around 350 meters per second. And let me jump down to maraging steel. That was the next material that was used back, and this would be back in the late 60s and the 70s when it was first used. It can get a higher speed. It was quite an advancement from aluminum alloys. And there's other materials, glass composites, titanium alloys. There's reasons why this is tricky. There's just problems in some of these. Titanium is one of them that it's doesn't work well with UF6. But the glass and Kevlar can work, but the material of choice is carbon fiber, which is readily available. It's used for a lot of applications, and it can spin higher than any of these. It can. I wrote down 700. The actual speed that it's spinning at in centrifuge programs is a secret, one of the people who works on our project came out of the U.S. centrifuge program and knows exactly what it is. So in our work, we often fuzz it up. But as I mentioned earlier, you can get up to 1,000 meters per second. Now, it's difficult to do that, very difficult to do that. And I'll talk about the Iranian centrifuges a little later, but there they have carbon fiber rotors in their advanced centrifuges, and they're limited to no more than about 550 meters per second, not because of the carbon fiber, but because of the other parts of the centrifuge that can't withstand what happens with the temperatures, in particular with these much higher speeds. And you need advanced materials. For example, I mentioned the scoop, the thing that the gas goes into. If you're at these very high speeds, it's much, much higher. And the typical scoops in an Iranian centrifuge are made out of aluminum. And at these high speeds, they would simply melt. And therefore, they would have to develop a whole nother type of scoop. And as far as we know, they haven't done that. Now, there's certain types of centrifuges defined by the length, and I'd like to introduce these. And I'll use these terms. The first is subcritical. There's something called homogeneous supercritical, and there's non-homogeneous supercritical. And the idea of a subcritical is really determined by a phenomena that happens. And it's how many of you have done experiments in physics where you have a string that's vibrating, and it vibrates at certain frequencies, and it looks kind of just like a blur. And then suddenly at certain frequencies, you'll get a big bowing. And then you can have a shape like this. You can have all kinds of numbers of waves. And those are called resonances. And those occur with a solid spinning object, where at certain speeds or frequencies, when this rotor is spinning, and if it has a certain length, then it hits a resonance that's actually going to make the rotor try to be like the shape of a banana. But if this is a solid object, you can imagine what's going to happen. If it bows out, it could hit the wall, it could break the bearings. And so you have to find a way to either avoid it, so these resonances you don't ever run into them, or to get through those resonances without having your centrifuge have its shape so distorted it breaks. And so subcritical means that you avoid the resonances. You just never hit them. And that has to do with making sure that the rotor tube is short enough so that when it spins up, it doesn't hit these critical, they're called flexural resonances. There's other resonances that happen in a centrifuge, and if you ever happen to see one operate, if you're ever in Germany at the Deutsche Museum, I think there's a new centrifuge museum that's being put together. There was an attempt to put it together in Augsburg. And they have centrifuge models where you can actually see when it starts up, you'll see it to shake a little bit. But those are different resonances, and they're not that hard to get through. These other resonances are much more damaging. Now, there's several programs, the US, the South African, decided to make the rotors longer. And so they're solid objects, and they figured out ways to get through the resonances. And it can be by allowing the thing to swing more, having more flexibility in the bearings. There can be other ways to do it. The Russian method, developed particularly by the Germans, and then commercialized by Urenco, and then copied by Pakistan and Iran and others, was to use the non-homogeneous supercritical idea, where what you're doing is you have a long rotor tube, and you put in flexural, or you put in, they're called convolutions, but they allow the tube to bend. And so it doesn't act as a solid tube when it goes through these resonances. And so it has more flexibility to actually bend and then get through the resonances. And pictorially, that's represented in this figure, where you see the bellows, where there's a convolution. It's a little hard to see in the graph, but in this case, it's pointing outward. There's reasons why you don't want to do that. Typically, they'll be pointing inward. And but this is an old, unclassified picture of a centrifuge. But the idea is the bellows allows you to get through the resonances. And that's not used in the U.S. case, for example. And they probably have the longest rotor tubes in the world. And they don't use any bellows. So there's different ways to do it. Here's a picture of, on the left is an old Zippa centrifuge. Very simple looking device made out of aluminum. It's 0.4 meters long. And the Russians developed something like that. Zippa was one of the captured. He was an Austrian scientist who was probably the most capable handler of a centrifuge. He could get him to work, and he could do that better than anybody in the Russian program. This is when he was there and active during the late 40s and early 50s. And so he was a real master at putting them together, getting them assembled, and then testing them. And one of the designs that he worked on, in fact, it was the last design he worked on, became the basis for the entire Russian centrifuge program. And you can see in this drawing on your right that the centrifuges are stacked and they're very short. So they're all subcritical centrifuges. And they built millions of them. And you can actually, it's like you can't see the end of the hall. So those are all centrifuges all the way down. The Zippa actually came back from Russia and developed this centrifuge with colleagues in Europe. He came here for a couple years in the 50s and contributed to the U.S. centrifuge program. But when they commercialized the centrifuge in Europe, they went a very different direction than the Russian. They decided that from a commercial point of view, you do want them longer. And so they went with this idea of the bellows in order to do that. And so an early European design is this, what is called the Iran's IR1 supercritical centrifuge, where it has 4 aluminum tubes with 3 connecting bellows. And this is a design from the late 60s, early 70s. And since it's made out of aluminum, it doesn't spin very fast. But by stacking it, they're able to get the total output up and get it up toward 2 SWU per year. It was developed by the Dutch, and it never really worked that well. It tends to break too often for a commercial plant. But it was the place, it was being developed at a place where AQ Khan worked. And so he was able to get a tremendous amount of classified information about this centrifuge. And this is what he sold to Iran in the 87 and in the early 1990s. Here's a set of Iranian centrifuges where the IR1s are in the sort of the second and third from your right, and then on the far left side is IR2M, I believe, and there it's 2 rotor tubes with 1 bellows in between, and it's 3 to 5 times more powerful than the IR1, and that has to do that it's made out of carbon fiber and it's just able to spin faster. So even though it's shorter, it's able to spin so much faster that it has a much higher separative power. Are there any questions on this? Yes?
Sorry, could you explain resonances just one more time, like the basic concept? So is it what happens when the string goes into a different shape? Or is
Well, no, the amplitude, it's certain frequencies where the amplitude they're going to add up. So there's, have you had physics? I mean, there's waves traveling down the string and back, and so certain frequencies the waves are going to add up. The amplitudes of the individual waves are going to add up. Often they're going to work against each other, where let's say one's coming through like this, the other's like this, and so it tends to cancel out. But there's certain times when they come together and their amplitudes will start to add, and that's when you get a resonance. And a similar phenomena happens with the rotating tube.
We have one more question from Henry. Why was the IR2M made shorter? What's the advantage of having a shorter one, less moving parts, perhaps?
Well, the bellows is a difficult part to make, and on the IR1, the bellows has a smaller diameter, and it's actually thicker, and it's where if you go to the IR2M, it's actually it's wider and the walls are thinner, so it's a much harder bellows to make, and that's one of the reasons. The other is any centrifuge is hard to get to work, and the IR1 is a proven design, and so they're in essence copying it, and they're having a lot of breakage. Now, the IR2M is actually, when Iran first set about making it, it was just with 1 rotor tube. And they felt at the time this is around 2000, 2001, they could not make the Moragian steel bellows for the IR2M, or what would be the IR2M. It would just be too difficult for them to do. And so they initially started with a subcritical carbon fiber rotor, and but then as they tested that, and you can see pictures of these subcritical advanced centrifuges in the Ahmadinejad visit in 2008. But after that, they decided they could learn how to make the bellows, And but that subcritical carbon fiber rotor, in theory, if it was spinning faster, would have an output of 5 separative work units a year. And that was their goal. So they basically designed their first advanced centrifuge, at least theoretically, to get 5 SWU per year. And but of course, as they actually use it, they don't get that. And so because they can't get the carbon fiber to spin fast enough. That's really the reason why. So with reduced speeds, then to get 5 SWU a year or so, they go to two carbon fiber tubes connected by bellows. Now the principal engineering challenge is really is posed by the high speed of the rotors. And again, if you can just imagine that at those speeds, any imbalance is going to wreak havoc with the centrifuge. And there's some other things going on I won't go into, but I'll mention and talk about the bearings. The bearings are very difficult to make in a centrifuge because they have to be able to move sideways, absorb vibrations of the centrifuge, and last for a long time. One of the ideas that in the Russian design was to try to simplify the top bearing. It's essentially 2 magnets, one attached to what's called the top cap of the centrifuge, one that's put into a fluid above the centrifuge rotor itself. And then the bottom one is a pin assembly that actually anything past about the 70s, it's in an oil bath, and the bearing ball at the bottom, and I'll show pictures of it in a second, it's grooved in a very special way so that the oil that it's in a cup and the oil's in between the ball and the cup actually rises up and so the ball is actually spinning on a film of oil. So there's almost no friction that it encounters. The original designs by Zippa were actually like a piano wire spinning in a cup, and the piano wire over time would just wear down. And but these designs that were developed are certainly much more effective. Yeah, you can. Well, I showed this picture earlier. You can see them a little better there. The schematic on the right side is showing the cutaways of the ring magnet that's involved in this, and so the bottom one is just a round ring magnet attached to the top of the centrifuge, and then the top one is in this oil and it's suspended by a little chain in this oil bath. And if there's any vibration, the vibrations can be transferred into the oil, and the oil is through dissipation. It's just the centrifuge can transfer its vibrations to the top ring magnet, and those vibrations are damped out by the oil. And that's an actual bearing housing, top bearing housing. Here's a ring magnet. It's a little distorted in this picture. They're actually made to very high tolerances, and if you're doing counterproliferation, you can find these ring magnets being bought, and one of the key things you're looking for are the tolerances, because these things can also be used in speakers. And you can use very sophisticated ring magnets in speakers too. So you can use crappy ones if you have a cheap speaker. You can use incredibly advanced ones if you have a very expensive speaker. But they don't have anywhere near the specifications of these of the centrifuges, and they don't combine the specifications with certain diameters that are specific to these Urenco style centrifuges. So you can catch them quite often. And these countries typically don't like to make them. They like to go out and buy them. It's cheaper. Now, we think North Korea now is learning to make the ring magnet that it would use. It's called alnico ring magnet, and so we think they're putting together or have put together the infrastructure to buy the raw materials to make alnico magnets overseas, but then to make the alnico magnet themselves and machine it to or get it to the right right size. Any questions? The bottom one, the pin, the picture on the right's a little hard to see. That's, I think, yeah, that's from the Ahmadinejad pictures, where the pin, the needle and ball assemblies is essentially screwed into the bottom end cap, and that's a picture of it. And this is, well, an actual one from seas someplace. I can't remember. Maybe it was in Libya. So maybe well, not sure. But anyway, this is the design. And partly when inspectors went in and saw these centrifuges in Iran, I mean, these are the kind of things that can jump out at you. I mean, why? I mean, there's the ball, but why is this here? And if you're just starting from scratch, you wouldn't think to put something like that there. It actually has to do with how the oil comes up when you're running it and you're trying to build a barrier so it's not going up toward the bottom end cap. So there were all kinds of indications when the IA first went into Iran, and Iran was saying it was all indigenous. We had no outside help. And then they're looking at it and seeing all kinds of indications that indeed they did. Did get quite a bit of help. And in fact, it is the Dutch design. Dutch centrifuge experts actually, I think they came to Iran, or one of them, or they looked at this. I think they had to come to Iran, and they looked at the designs that Iran had, and were able to tell that it was there. It was close, if not exact, to the Dutch design. On the right is the cup, and the schematic below gives the idea of what's happening in the cup, where the cup is in an oil-filled cavity and is held up by springs, and that gives it this ability to move. And again, the oil will dissipate the vibrations. Now, one of the surprises in all this is that these little balls turn out to be rather complicated to make. And yes?
Does Iran produce all of this indigenously? Do they have the machine tools to make
Well,
components, their own centrifuges?
You have to define that well. They have to make the components, but they're often using subcomponents bought overseas, or they're buying the carbon fiber overseas and then using a winding machine to wrap the rotor that was bought overseas. So it's their infrastructure is filled with foreign procured machine tools, and they depend very much on getting raw materials and equipment from overseas. But technically, they make the centrifuge components. And here you can see the ball is welded to this needle, and but I haven't seen this in Iran. This one is a Pakistani effort to buy that ball, and that's a more advanced centrifuge program than Iran, and they apparently still go out and buy the balls. We know in the past they always did, and if you look in the Libya case, there was a Dutch member of the Con Network who bought all these balls for the Libyan centrifuge program, and but here it's distinctive feature is that it's 4 millimeters in diameter. That's very distinctive to a Urenco centrifuge, particularly a P2. But what happened is the Dutch one had a smaller ball originally. It was 3 millimeters, but they learned that if you make it a little bit wider, like they did with it was actually a German design that is the basis of the advanced Iranian design, it'll last longer. And so you look for this, and you look for the numbers where they're buying many thousands at one time. So here it's a case, why can't they make this? And I would imagine if they really worked hard at it, they could. But they don't want to invest the money, and they also need better mechanics. And it used to be in the old days when this was long before there was the modern computer numerically controlled machine tools. Very few people in Europe in the Urenco program could make a bottom bearing, could make the cup and the ball and get it all to work. And there are just a handful of machinists who could grind these things accurately enough for a centrifuge. And in fact, the British, another example of foreign dependence, the British Urenco program was making these things initially and then said, nah, it's not worth it. And they contracted with the Germans early in their program to make all their bottom bearings. I'd like to. Are there any questions on this before I move on? Yeah.
Those steel bearings are just normal steel bearings, 4 millimeters, because you can get those anywhere. You can go to Home Depot and get.
No, not to these specifications.
That precise?
Yeah, and we're just researching this for another project. Maybe we'll know an answer next week. I don't know how specialized the steel is per se, but the roundness has to be is unusual, and they're not easy to make. No, it's the same thing with the ring magnets. You can go to Radio Shack and buy ring magnets, but they're not going to have the specifications. And the specifications are both in the size, but also in the magnetic field. That you have to have a very uniform magnetic field that's generated by these things.
That's what wipes out the computer. That's why you can't.
Oh well, yeah, we have one actually, but
Yeah.
it was one from the Iraqi program.
I know where it is.
You want to get it? I mean, but keep it away from the computers. I mean,
Do you know where it is? Okay.
Do you know what they're made out of?
It varies. The simplest ones for a P1 can be made out of ferrite,
Oh, okay.
and it's just machined to high specification, very cheap. And the more advanced ones, like the P2, like the IR2M would use an Alnico magnet. It's going to be a heavier because you're holding up part of the weight with the magnet, and so when you go to Miraging steel and a larger diameter, you're just going to have to hold up more. And then you can use cobalt samarium, and there's other materials too. And a lot of these programs change. I mean, the Iraqi program in the 80s was trying to use Alnico and cobalt samarium, which is also very indicative of centrifuge program. But Mehdi Ubaidi, you may ask him, at the end he was thinking, we're going to go to ferrite because no one looks for people buying ferrite magnets. And they were trying to always think of ways to better hide their program. And, but here, this would be one that actually Mehdi's colleagues ordered out of Europe. I think it's out of Europe. Maybe this is Chinese. I'm not sure anymore. But it was to very high specifications. Why don't you take it away? Because I mean, this thing can wreak havoc with.
Yeah, I had to put my cell phone away.
I'd pass it around, but if you have cell phones and things like that, it's. Well, I mentioned that when you run centrifuges and you run them alone or you run them together in cascades, you're not going to get the enrichment output that you would derive theoretically. And it's just a fact of life. And what we learned in the Iranian case was that these IR1 centrifuges run by Iran can have incredible inefficiencies. And some were induced by Stuxnet, but some are induced by the fact that the centrifuges break. They can break 5-10% of it can break every year. And if the centrifuges are in cascades, it's going to cause disruptions in the ability of that cascade to enrich uranium. Now here's some typical examples. So let me just focus on the IR1. In single machine tests, it can get 1.4 SWU per year. What we routinely measure from the IA data, and there'll be another IA report out tomorrow, the best they're getting is about 0.9 SWU per year on average for an average centrifuge in a production scale cascade. And right now I think they're more down toward 0.8. Sometimes they'll go higher than 0.9, but not that often. And then the P2, which is 2 Miraging steel rotors connected by a bellows. And typically, rotors connected by a bellows, but in practice what you do is make a long rotor tube that's the length of 2, but make it as 1, and then put the bellows in the middle. And what I'll do is I'll hand out it was an Indian centrifuge design of this type. And I'll just, there's a schematic, or actually it's a design drawing that shows what's going on with the bellows. The last entry in the table, well, the IR2M, the second to last, it's about, the idea is with reduced speeds to get about 6 SWU per year, but it's unclear if they're going to do better than 3. Or let me put it this way, they'll probably do at least 3, but they may be very close to 3 in the end. Because of the inefficiencies, but there's not a lot of data now to decide. The P3, which is a Pakistani nomenclature, it was another design that Kahn stole. Is actually 4 Miraging steel rotor tubes connected by 3 bellows, and it would have a single machine value of about 10 SWU per year. And we think Pakistan has built those. But this inefficiency is just something you have to live with. I covered this last week that with these kind of centrifuges, a single machine can enrich significantly or produce the necessary quantity of enriched uranium. And so you need to arrange the centrifuges in series to reach the desired enrichment level, and you need to arrange them in parallel to give the desired output. And as we discussed, that's a cascade, which you're all familiar with. And here's an ideal cascade arrangement where if these were centrifuges, the stages go this way. So each one of these is connected in parallel, and those represent the stages where the waste comes out here, the feed goes in here, and the product comes out at that end. And so the stage size is, in a sense, is longest or tallest here, and then it diminishes as it goes to either end. And that would be a very typical shape of an ideal cascade. And I'll try to generate another. There's another picture. I couldn't find a good one today, but someone down at UVA is trying to generate one that has the numbers in it, so it's a little easier to work with. But as a definition of ideal cascade, this slide gives you about all you need, and there's certain characteristics, and a lot of it has to do with being able to calculate. And so in an ideal cascade, what's called the separation factor, it basically says how much enrichment takes place from one step or stage to another, that's fixed at every stage, which actually cannot be achieved. And then we talked about last week the idea of mixing. It's coming from the upper stage and it's being combined with material from a lower stage, and in the ideal cascade you assume that they have exactly the same enrichment, but in reality they may not, and so then you get mixing. And so if it was whatever it is, 3.4 coming down from the top, and it's 3.45 coming up from the bottom, the mixing would make it 4.25, and so you lose some of the enrichment that you've already produced. And also, an ideal cascade is the most efficient arrangements of centrifuges. So when you're planning things, it's useful to have this concept in this, because this is as good as it's going to get. And as I mentioned, the mathematical calculations are much easier to use, but it can't be achieved in practice.
David, quick question from memory. Are there any videos of centrifuges operating online? And also, is there any place we can see it in person without having to go to the German museum?
I tried to bring back one of Zippa's centrifuges once, because I don't think there's any in this country. I mean, but it just didn't work out, and he ended up giving it because he had one at home. I mean, and then there was, he had one at home that had UF6 on it. It had actually been operational, and he disassembled it and brought it home. So you could get UF6 can burn you. It reacts. Fluorine is very reactive. So he's old school. He was old school. So and then there was a model at a German company that was the main contractor to make the centrifuges for German Urenco, and they were put out of business in the 90s, and they had a model, and that became available, but I couldn't get it. So I'm not sure where you would go. And these are, the one at this German company was called MAN New Technology, is a model. I mean, it had a cutaway, it couldn't work, but you could really see it. And I talked about these simple resonances, not the serious ones, but you could actually see the thing as it spun up, and it was spinning up at a very low speed, but you could see it encountering resonances and shaking and then getting through them, so it was a nice model. Typically, the manufacturers and operators of centrifuge plants are very private and secretive, and so mostly what you get are these kind of pictures, where you see the outer casing essentially, and these are water pipes. They're helping control the temperature along the inner wall of the centrifuge, and that creates this countercurrent flow. And there's all kinds of designs. Some of the Iranian centrifuges have water tubes only at the top, some at the bottom. And just some, you don't even need them. I mean, there's ways to do it without any water tubes. But here's a typical cascade, old style, where you have the piping coming out the top for the feed, product, and withdrawal. There's some bends in it to help with vibration. And it goes into some central piping. Well, you can see the three pipes in the background running parallel to the floor. That would be the subheaders, or what are called subheaders, just big pipes that carry the gas, whether it's product tails or feed to the next stage. Yeah, here's just another one. Let me see something. Let me jump ahead a second. That's an overhead picture of Urenco cascade. They're always very nervous, though. They don't want anyone to know the height of their centrifuges. So this is not an atypical Urenco picture where you get to see the top of the centrifuges in the piping. And then these are the three pipes, product, feed, and waste. And there's something called a dump tank, which is in an emergency. It allows the gas to be evacuated from the cascade. Let me go back up, come back to that. Here's an arrangement of centrifuges in a cascade. And this is a Pakistani design in quotes, indigenous Pakistani design, probably, I think, designed by Europeans who were working very closely with the Pakistanis. And this was involving 344 of these P2s, and the feed is here, and so it's stage 11, and here they're starting stage numbering from the product end. They don't always do that, but from the product end and then going up. And here's 15 stages, and the feed stage has 42, and then the product end only has 2. And this, again, one of the problems the Iranians faced, I'll come back to this too, is what if these break? And typically only one is enriching, the other is a spare. But what if both break? That you're not, if you're trying to get whatever it is, 3.5% enriched uranium, you're simply not going to get it. And that material is going to, at lower enrichment, is going to go into the product tank. A lot of these cascades will have one product tank. And so because you don't enrich up to 3.5, you'll come up maybe with 3.1 or something. That'll go into the product tank and dilute it as the product. And so that would be an example of an inefficiency. driven by cascade or centrifuges breaking. Because of that, the Iranians are pretty adept at taking out the broken ones and putting in new ones. But nonetheless, they can't, particularly when Stuxnet was most active, they couldn't keep up. And so I shouldn't laugh about that. But this is a nice cascade to go from natural uranium up to 4 to 5% enriched uranium. It's also what the North Koreans have in their Yongbyon plant. At least the first section of the Yongbyon plant has 6 of these, and that's information from the North Koreans.
6 full cascades.
6 whole cascades, which also tells you that building at Yongbyon is to make low enriched uranium. It's not designed to make weapon grade uranium. We don't know what's in the extension, and there's been news stories about recently that somehow they've detected thermal signatures showing it's operational. This is an IR1 cascade. This was part of a Stuxnet study we did, because we noticed, I forget who noticed it in the code, but they noticed that there were these numbers associated with a grouping, and we had the actual cascade arrangement for the IR1, which was not public at all. We were the first to make it public, and that was one of the indicators that Stuxnet was going after Natanz, because this is a production scale centrifuge at Natanz. And here again, this is the product stage. There's 2, but one enriches and one's a spare.
So just with product stage, feed stage, and tail stage, what exactly does that mean? Like product stage means like at that stage.
That's where the enriched, the final
You
enriched
have
uranium.
product.
Yeah, and it goes out in a pipe to a product tank. And I'll show this in a minute. I mean,
Okay.
I'm tending to build it up from the little to the bigger. So we'll get to I'll show you some schematics and product tanks.
So the first stage, the whole thing would be 1E.
Well,
where you turn the heat.
yeah, this is, and again, the numbers vary, but this is the feed stage. And that's where the natural uranium goes in. And it'll be the largest stage. It'll have 24 centrifuges.
Okay.
So if we go back to this picture, that one, I think the first one is a little more intuitive. If you go back to this picture, this is what's happening. It's going into that. And then each stage will have an output. Enriched uranium will go out, and that'll go up to this stage.
Okay.
And then the waste will go down to this stage.
Okay.
But this stage then will also have an enriched uranium output.
Okay.
It's kind of a mini product.
Thank you.
So it helps to think of it like a sort of, for lack of a better word, a cycle, where the feed is being introduced not at like the very beginning of a cascade, but rather where that series of centrifuges is the largest.
Yeah.
Okay.
Yeah, and this is, I'm not sure this is helpful, but this is another schematic where here the feed goes in. These are actual schematics of centrifuges. And then it shows the red is product. And here, green is the depleted stream. And so the red and green combine to make blue. Does that actually happen? Does red and green make blue? I don't think so, right?
No.
This was done by an engineer. Sorry. But anyway, if you look at this will give you another idea that here here's the waste. The final waste comes out here. The product, whatever it is, 3.5%, 90%, whatever it is, comes out there. And then here's the intermediate enrichments from stage to stage. Any questions on that? And we can come back to this. I mean, this is probably too complicated. I mean, it's also one of Urenco's frustrations is if you're not careful, you can have a disaster in the piping. I mean, it's not obvious how you pipe all these centrifuges and get the stages to work. And they came up with a very clever idea, which A.Q. Khan acquired with some German help, and it turned out the information wasn't classified; it was only proprietary and export controlled, and so it's now at a higher, it's protected at a higher level now, but the secret got out in essence, and all these programs use this same cascade design. And it's all based on making low enriched uranium, and so they had to modify it. And I wanted to show this, but I'll leave that to you. There, you can actually, typically when they show pictures of cascades, this is a large cascade. They'll show the first stage, the feed stage, and it's a lot of centrifuges. This figure shows where the stages are changing and so the product, the product of one becomes the feed of the next, and so they have this bent tube arrangement, and you can actually see it over here if you look carefully, that you can see where the stages are changing. So I'll leave that to you. But again, these weren't obvious ideas, and a lot of the reasons these proliferate states can actually have these centrifuge programs is that they obtain so much what rightly should be classified information. If they had to do all this on their own, develop the centrifuge, research the centrifuge, develop it, deploy it industrially on a demonstration scale and then on a production scale, it would have taken them decades. And they would have had to, on their own, come up with the piping arrangements and get them to work. And that's been one of the problems with centrifuges, is that no other enrichment technologies leaked like this. And unfortunately, it came with help, human help. And Mady had tremendous help. He doesn't like to talk about it, but he had 3 top German centrifuge experts, plus industrialists, anxious to help him, providing classified documents. There's actually a 4th guy we've never been able to identify, who was inside the program, and they could task him to get the classified document that they wanted, and he would bring it out, and then the Germans on the outside would give it to the Iraqis. And that was critical in their success. Well, I mentioned that they stole or acquired the low-enriched uranium cascades, so they had to go in Pakistan, and then in other countries, they have to think, well, how do you make weapon-grade uranium? And so they came up with what we call step cascades. And in theory, you could design a cascade that starts with natural uranium and is long enough, has enough centrifuges in it to go all the way up to weapon-grade uranium. But it's going to require a huge number, maybe 2,000, 3,000 of these IR1s. And that's risky because I mentioned last time if a centrifuge rotor breaks, it creates it's like shrapnel, and there's a lot of pressure, a lot of temperature generated by this, and that creates a pressure pulse which then goes down through the piping and can just take out one centrifuge after another. And so you tend to design cascades that are shorter, so that not so much as at risk. But in theory, you could have one long cascade going from natural all the way up to weapon-grade uranium. But Pakistan didn't want to do it, and it came up with this idea of a step cascade. And what it is, it's more expensive, it's less efficient, but you basically are dividing up the process of going to weapon-grade uranium into steps. So you have a very good design to go from natural to 3.5%. Well, then it turns out you can use that same design to go from 3.5 to 20, and then you have another set of cascades to go from 20 to 60 and 60 to 90. And so the idea is this was in the Khan information. I think this was the design for Libya. And so 4 steps. The first one is going, in this case, it was making 3% using natural uranium. It had this very generic value of 164 machines per cascade. And there would be 32 cascades just making the 3%. And then there would be essentially 14 others that went all the way up. So there'd be 8 exactly the same design cascades that would go from 3% up to 20%. And Iran has done these 2 steps. They did it a little differently than just using the single cascades, but they essentially have worked those 2 steps. And then you need 3 cascades of 114 centrifuges here. These are good, they're P2s to go from 20 to 60, and then you need 3 to go from 60 to 90. So you have a total of about 7,100 centrifuges, and 70%, most of them are just making LEU, 3.5%. And there's all kinds of variations on these. You can just use cascades that are 164. You can actually just use the same cascade to go to the 3rd and 4th step. You can combine them in the way the Iranians did, which are called tandem cascades. Run 2 together. They work together, a pair, and
really quickly, how long does it take to reorganize? How long does the reorganizing process take? And are the centrifuges being reorganized the same centrifuges or different?
I mean, it's Henry, it's $1 million question. We think, the group of us that have worked on it, that Iran could reorganize in the cascades to use this step process in 2 weeks. So that it requires some preparation, but they could reorganize. Now they don't have to reorganize the cascades, but they have to reorganize how they're enriching uranium, organize the feed and product tanks, and some of that I'll talk about here. But if you want to go to tandem cascades, we thought it would take a month, but information that I learned in Europe from governments this summer, they think it can be done quicker. And so, and they think that Iran, if it was going to break out, would actually do what it did from going from 3 to 20. They would actually put them into tandem cascades. So that going from 20 to 60 would be tandem cascades, and 60 to 90 would also be tandem cascades. But they think that the switchover can be done a lot faster than we think. But it could be, with practice, and you could practice someplace else, you could potentially get it down to a week or 2. Now here's a centrifuge plant schematic, and again, it's I didn't bring any pictures of these things. I have some pictures of equipment, but what happens, and this is a plant essentially to make low-enriched uranium. The uranium hexafluoride comes into the plant in tanks, and at room temperature or regular temperatures, pressures, the uranium hexafluoride is a solid. And so what you do in a centrifuge plant is you put it in an oven or an autoclave and heat it. And by heating it, you then turn it into a gas, which then is fed into the cascades, it goes to the feed point. And here, this is another way to represent an ideal cascade or a cascade. It's got a tapered shape. And so here the feed comes in, and then the product is going this way. And here, as it gets redder, the enrichment level is increasing. Here, as it gets greener, it's more and more depleted. And then the product then comes out. Now, this is a Urenco design. I'll show this is a newer Urenco design. And this is actually for Dan. A roots pump run backwards as a compressor. And so in Urenco plants, they take the gas coming out of a cascade and they run it through a compressor, and then it's deposited into, in this case, it's the depleted uranium tank. Up here, it's the product tank. And so it's a very simple process. That's been the Urenco design for over 30 years.
So that's the primary use of it?
That's one of them. It's also this is all operating under vacuum, and so the roots pumps it's a vacuum pump, and it works within to create the vacuum. Yeah, and let me just say that again. I mean, a centrifuge plant, or inside the piping, the centrifuge, it's all under vacuum, and so you use vacuum pumps to create that vacuum. the design in Iran is a much older Urenco design, and what it is, again, it's the terms are different. Here they're using steam to heat the autoclave or the tank. It just has more. You have to reduce the pressure. It's fed into the cascade, the same shape. The product comes out, and it actually goes. It's chilled. So the gas goes into this tank. It's chilled and it solidifies, and it just builds up over time. When the tank is filled, they then turn on some heaters, and then liquefy it, and then drain it into a product tank. And so that's what's happening here. So they drain it into a product tank. Here it's cold air, it solidifies it again. And here it's the same thing. With the depleted, it goes into it's called a desublimator. I call it a desublimator, desublimer. I don't know. But it goes in, the gas goes in, it's chilled, it solidifies, and then when the tank is filled. And so in an Iranian plant, there would be typically 3 of these in a row. So you fill one, valve it off, and then it dumps into the next one. So you're operating continuously, even though it's a non-continuous process. And this is the older design of using these, and they're called cold traps. So in some discussions, you'll hear about cold traps. We worried, there was a scare that they may have been switching out the cold traps for compressor system, but so far no one has seen it. But at some level, if you're going to make weapon grade uranium, you would like a compressor system, because you can. One of the problems with weapon grade uranium, it can go critical. If you have a lot of it, 20, 30 kilograms of it in a container, you have to worry that the chain reaction could start, and you'd have a small little bare reactor in your centrifuge plant. And so if you're going to break out, you have to worry about the size of these tanks in the cold traps. And if you had a compressor system, then you're just pushing the gas into a tank, and you can control the size of the tank. It can be a very small one that could only hold, let's say, 10 kilograms of weapon grade uranium. So there is a nervousness of whether Iran has learned this compressor system, because if it had a clandestine plant making weapon grade uranium, that may be a better way to go. Or if it could use Natanz to make weapon grade uranium and then bring in a new system like a compressor system. I'm going to skip over these. I'll leave. These are just a listing of equipment, and it's relevant for counterproliferation, but I don't have time to cover it, but I'll leave it to you. Just the various equipment that goes into these various parts of the plant. And in our work, it's more important than. Here's a picture of these autoclaves. Yeah, these were, these are 3 autoclaves, and they open at the end. The tank goes in, and then they're heated, and then it goes out by pipe work. This doesn't look connected, right? Maybe this is from South Africa. Is that possible? South Africa was the node that was contracted by Khan to make all the feed and withdrawal systems for the Libyan plant, and maybe that's from there. It must be, because this is. Yeah, so this, I guess they set it up. After they made it, they set it up. And so here's what would be the feed and withdrawal system for this Libyan gas centrifuge plant. And then they boxed it all up and put it in shipping containers. Yeah, here's that's the inside of an autoclave, just a small one. So that would be for a smaller cascade for research and development, or for higher enrichments, where you have to have smaller tanks. I just want to do something quickly. This is sort of in this flavor of what's in the news, and I find the Iranians generally confusing when they talk about anything technical involving centrifuges, and they've managed to add a lot of confusion to a discussion of SWU, and I'll see if I can and if I can clarify that, and that's the intention of this, is that we last week talked about measuring enrichment efforts in this funny unit, kilograms of uranium SWU, or SWU for short, and that's where the trouble starts. It's using SWU for short. There's another unit which is used not as often, but it's actually kilograms of uranium hexafluoride SWU, or kilograms of UF6 SWU. And the SWU unit, as I mentioned, is complicated, but it's dependent on the mass flowing through the centrifuges or through the cascades. And because it's a mass flowing through and it's uranium hexafluoride, you have a choice. Do you want to measure the mass of the uranium, or do you want to measure the mass of the uranium hexafluoride? And either one is legitimate, although typically they use uranium. That's the more common unit. But if you don't say which one you're using, then that's where the confusion comes from. And so we found that Iran often gives their flow rates in their calculations in kilograms of UF6, but they then just use SWU when they discuss their actual values. And the difference between the units literally is the difference between the difference in mass. So uranium is about 2/3 of the mass of uranium hexafluoride. And so if you know what's going on, then you just have to, if you look at a uranium unit, just multiply it by 2/3 or 0.667 or 0.67, and you'll get the answer in the more common units. And what they did is, and maybe you remember this, the supreme leader, I think it was in July, he said Iran has to have 190,000 SWU. That's their red line. I mean, they have to be able to have a centrifuge program that's going to be 190,000 SWU, and that actually shocked people because it was a lot higher than even what they'd ever heard before, which is enough to fuel the Bouchier reactor. And but if you convert it, that if you interpret it as kilograms of UF6 per SWU, then you get down to 130 kilograms of uranium SWU, and that's essentially what you need for the Bouchier reactor. But if you want to do the number of units or centrifuges, if you just convert by using the 0.9 kilograms of uranium SWU per year, you then divide that into 130,000, because again the units have to match. You'll need then what the supreme leader is saying is that he feels it's the right of Iran to have 130,000 IR1 centrifuges, and of course that's compared to the U.S. position at that time of having 1,500. And so when they talked about the impasses, this was one of the fundamental ones. And I heard from the people in the negotiation that this poor ambassador or foreign minister Zarif had no idea this was coming. But it was the supreme leader said it. So it becomes the position of the negotiating team. And so one of the reasons it kind of stalled out in July was, from a U.S. point of view, Zarif had to go back and get some better negotiating instructions. That there's no way they're going to have 130,000. Now, the mistake would be, if you divide the 190,000 by 0.9, there you're mixing the units, and you would end up with 211,000 centrifuges. So anyway, I hope this made it clear. But units do matter. And in daily life, I mean, if someone just says that car is 6, doesn't say 6 feet, meters, whatever. I mean, it's a little bit of what's going on here.